This unit that we're going to start now is dealing with forces. First thing we need to do is define what a force is. If you think back to elementary school, you defined forces. You remember how you defined it. Hopefully you remember that when you defined forces, you called it either a push or a pull. When we talk about forces, we talk about two different kinds of forces. The first kind of force we're going to talk about are long-range forces. Long-range forces, as the name implies, act over very large distances. Another thing that's true about long-range forces is they don't have to be in contact with the object they are acting on. Because they don't have to be in contact with the object that they are acting on, because they act over large distances, essentially a long-range force we can think of as a force field. If you can think of examples of forces that fit into this category, we've talked about one already. When we have something that's in the air that's being held and you let it go, what happens? What we learned in this unit and the previous unit was that it falls. Something's causing it to fall, something's pulling on it. So we have gravity exerting a force causing it to be pulled down. So gravitational force is an example of a long-range force. We're going to use the symbol F for force, and F sub g is going to be gravitational force. Another example of a long-range force is a force that you may have used or that you've seen before when you play with magnets. You can chase one magnet around with another magnet and not have them touch each other. Since they aren't touching each other, we have a long-range force. So magnetic forces are long-range forces. A third type of force, one we're not going to study in this class, they talk about it in AP Physics, is a force that you deal with primarily, or you get to experience primarily, in the winter when there's not much moisture in the air. And that's when your socks stick together in the dryer, or you can get a balloon to stick on your pet or your sweater. And that would be electrostatic force. So those are the three types of long-range forces. There's one other one, there's nuclear force, but we're not going to talk about that. And really in this class we're only going to deal with gravitational force. The other kind of force we're going to talk about and spend more time with are contact forces. As the name implies, you have to make contact with the object in order to apply this kind of force. So this is truly where I see the pushing and the pulling going on. Examples of contact forces would be applied forces. So it's just a subscript for A for applied. If I'm pulling on something, usually it's a rope or a handle or a chain, and I'm exerting tension on that rope or cord or chain, and so that would be a tension force. When I have one thing sliding against another thing, that creates a type of force. That is a friction force, and that is a contact force. And there's one more force that we're going to talk about called the normal force, and we'll get to it in a few minutes. So those are examples of contact forces. Forces are vectors, so that means you have to include direction and magnitude. The symbol is F. The units, newtons. Newtons after Sir Isaac Newton. Let's take a look at Newton's first law of inertia and look at an object, first of all, that's at rest. An object at rest isn't going to go anywhere unless we apply a force to it. So there it is, sitting there minding its own business, and I'm going to apply a force to it. My foot isn't the only thing that applies a force to it, because it slowed down and it stopped. So what's the other force acting on it? If you said friction, you're right. My foot applied a forward force. Friction applied a force to slow it down. And it traveled in one direction. It traveled in the direction that my foot applied the force. And friction acted opposite the direction of motion. Now what happens if we take friction out of the picture? Let's do that by turning the air on this thing. And now the airflow will cause it to be frictionless, and it will obey Newton's first laws without having that friction force present. If the air jets were perfect and the floor were flat, it would just stay in one place and spin. It's kind of doing that right now. If I apply a force to it, it should move in one direction, it should move in a straight line, and it should move in a constant velocity. Let's see if that works. It hit the wall and it bounces back. Straight line, constant velocity. When I tap it, it moves in the direction the force acts on it, and it moves at a constant velocity, relatively speaking. If you apply a force in a different direction from the direction it's moving, the direction it will follow is a combination of its original path and the direction the force was applied to it. So the velocity doesn't change except right after the force was applied. While it's traveling, because there's no friction, it's going to travel at a constant velocity. And it will only change direction or change speed when a force is applied to it. And that's what Newton's first law is all about. Laws regarding forces, we're going to take a look at the first law and the third law with this unit, and we'll look at the second law in our next unit. First law, remember what the first law is. Object at rest, object in motion, all that good stuff. So if we want to put it into written form, Newton's first law says an object that's at rest, and we're going to expand this to say an object that has constant velocity behaves just like an object at rest. And this object is going to tend to stay at rest or tend to stay at a constant velocity until another outside force acts on it to change its behavior. Another way of talking about Newton's first law is to say that an object resists change in motion unless sufficient force acts on it to cause the motion to change. This resistance to change we call inertia. So the bigger the object's inertia, the more force you need to cause it to change, either to start moving if it's at rest, or to slow down if it's already moving, or to speed up if it's already moving, or to stop. So the amount of force you need to apply is directly related to the inertia, or how much force you need to apply to cause an object to change its behavior. We're going to take a look at what happens when we put some books on a board, and the force the books exert, and the force the board exerts as well. If I look at this board, right now it is just resting on some bricks. What I'm going to do is I'm going to start stacking some books on the board and see what happens to the board, the shape of the board, and the books. If I stick the first board on the book, not much happens. The book is pushing down on the board, so exerting force down because gravity is pulling on the book, but the board is preventing the book from falling to the ground, so the board is pushing back up on the book, or exerting a force upward on the book. If I put another book on, now I start to see a little bit of change in the board. Again, now I have both books exerting force down on the board, and the board is able to prevent both books from falling because it's still pushing up on both of the books. If I stick a third book on there, and now even a fourth book, let's put the heaviest one on top. Now I've got the board bowing quite a bit. I've got 4 books pushing down on the board, and the board is pushing up on those books. So each time I add a book, I have more force pushing down, which means the board has to exert more force upward. The force the board is exerting upward on those books is called a normal force. Normal force is a force that is responsive to forces acting on it. Normal means perpendicular to, and so the normal force is perpendicular to the surface of the board, and it's acting upward on the books. We're going to focus on the force that the board exerts upward on the books. If there are no books on the board, no force is exerted. The force the board exerts upward on the books is called the normal force. And we saw the symbol earlier, it's F sub n. A normal force is a responsive force. That means that it's only as strong as it needs to be. And as we saw in the demonstration, the more books I stacked on the board, the more the board bent. It didn't break. So that means it was pushing up on the books with a force that matched the force the books were exerting down on the board. Because the board didn't break, the force it was exerting upward after I add each book was greater and greater. Normal means perpendicular to the surface. So a normal force is perpendicular to the surface that it's acting on.